Part 2 of lecture 24. So in the previous part, we talked about what is the structure of a recurrent neural network. And in this part, we're going to talk about how to train these. And as you expected, we're going to use gradient descent. And we are going to give it a fancy name. It's basically a chain rule, but we're going to call it back propagation and through time. And it's basically just chain rule. And we're going to take derivative of the hidden units with respect to the hidden units in the previous time period. So that's why there's a through time part. But again, it's the same procedure, same idea. We just have longer chains over time. Well, I guess mostly that's the main difference. And we're going to use the same gradient descent update to update all the weights. So there are more weights because there are weights connecting the inputs and the hidden and the hidden in the previous period or the previous time step, and then also hidden and output. So we have 3 sets of weights, but that's basically it. And also that's all you should know, because obviously I'm not going to put any of these things on the exam or in the homework, and you don't need to implement any of these. You just use packages. So if you are not interested in the technicality, the specific algebra, then you can just stop here. And also you don't need to watch the next part as well, because there are some other additional technicality about the gradient descent as well. So okay, that being said, let's get started if you are interested. So let's first look at the network structure again. So what I had at the beginning is called the unfolded network. So the standard way to represent the network is actually the way with the recurrent unit. Is basically H goes back to itself, and we don't have the time index for these. And I have drawn a diagram like this in the previous part as well, but the unfolded one is basically just unfolding this recurrent relation, and it's basically we're making it h1, h2, h3 at different time steps, so h4, and we have our x input, and we have our y outputs. And of course, these y's will generate some kind of cost. So what's the difference? Let's see if we want to figure out the weights here, the weights between the first unit of the input and say the first unit of the hidden unit. There can be multiple hidden units, and we're just writing it as one. So suppose we want to figure out the derivative of C with respect to W11. Why is it difficult? Because we can just go back, and go back, and take the derivative of each and then just multiply them using the chain rule, right? The problem is that this is not the only time W11 appears. They are sharing the same weights over time. So all of these are basically the same W11. So every time we update it, we need to consider all of these possible ways that W11 change will cause C to change. So in particular here, it means we need to consider the path going back this way, this way, this way, and also this, and this and that. So we need to consider all of these derivatives, and then we need to add all of them up. And not only that, we need to consider this path, this, and this. So you can probably see that we can do that again with all the previous ones. So we have basically, the problem is we have lots and lots of different chains that can connect this particular weight with the cost. and we need to add all of them up. And actually, that's not the only tricky part. We can store some of them because some of these are reused many times, so we can store the information. They are the same derivatives. So there are some tricks to make the computation faster, but the main idea is that you need to add up all of these things, all of these derivatives, and then sum it up to get our dc dw. And how many groups of w's do we have? One here, we will call it w superscript x, and one group of, basically one matrix of weights here, wy, and one matrix of weights here, wh. So that basically summarizes the problem that we face, and then maybe we can go through a specific one with, say, 2 time steps. So let's actually write it like this. x1, remember we first have these z's, z1, and this is the hidden layer 1, and it's connected to a1, and a1 is connected to z. Let's use superscript y to mean the output linear part, and output activation 1, and then we have our c1, cost number 1, and then c1 is connected to c. C is also connected to C2, and C2 is connected to A2Y, A2Y, Z2Y, and A2X, C2X, X2. So how are these linked over time? So the important thing is that we are linking only the hidden units, and we're using the previous time step activation and link it with the current step linear part. So we don't have like all of these other ones. So that's basically the structure. So let's see what each part of this would do. So first, the derivative of c with respect to c1 to 3 is just 1 because c is the sum of all of these. So it's just 1. So that's very simple. We don't need to take any derivatives. And c with respect to a is that softmax thing. So softmax, remember, it's usually something like ai, here ai minus yi, or something similar to that, if we use one hot encoding for y. And there is this thing divided by ai, 1 minus ai, and that will be cancelled out with this derivative, which is ai 1 minus ai. So these parts are cancelled out, basically. And so you only get these ai minus y thing left. And next is a with respect to z. So that's basically, this derivative is just a w, and it's w in the upper layer. And in between these is the derivative of the hyperbolic tangent. I think I spelled this wrong. Tangent hyperbolic. And the derivative is something very simple as well. So it's not ai 1 minus ai, it's a1 minus ai squared. So here ai is axi squared, so that's our derivative. And suppose we want the derivative here, we get our first chain, and the derivative of z to x with respect to some w that we want is just our x2 or x2j, depends on which one we want. Okay, that's our first chain. And second chain is we need the derivative between these two as well. And the derivative between a z and the a is just a w. So this is our wh, and whichever jj prime thing, that it depends on which one we want. But in any case, we need to go back here again, and the derivative between these two is again hyperbolic tangent, so it's 1 minus ai x and square it. So the difference is this is a1i squared, this is a2i squared. The notation is actually not good. Let me change it. So this is a something 1, this is a I something 2. And at the end, when we take the derivative of this thing with respect to x1 now, for the same weights, we get x1j or something like that back. And we just add up these two chains, right? Each chain is basically a bunch of derivatives multiplying each other, and we just add up all of these, and we're basically done. So in the next few slides, I included all the formulas that we talked about. So if you want to take a look, I don't actually know why you want to do that, but I included this just in case. And likely there will be some typos. So if you find any, you can tell me. But okay, that's basically all I want to say. And okay.